And we're back again with part 3 of the SuperPET restoration. When we left off in part 2, I had got the PET side working, but the 6809 SuperPET side was not showing a picture. Well, there have been a few developments since then, and I'll walk you through what's changed since the last video. Eagle-eyed viewers might notice the system's only showing half the RAM it should be. But the good news is, if I switch to 6809 mode, it works now. So what happened? How did I get the SuperPET side working? Well, I'm sorry you missed it, but I'm embarrassed to say that all it took was reseating this row of EEPROMs. I pulled those out to read them in my EEPROM reader to make sure they were good, and when I put them back, the system just started working. That really should have been the first thing I did when I was troubleshooting this thing in the first place. Always reseat the socketed chips. Also on the plus side, thanks to the kindness of a friend, I now have a proper MOS ROM chip to put in the kernel ROM socket, and I can do away with this EEPROM and adapter socket. So what about the RAM? As you can see, the system's showing all 32K of memory now. And if you remember back in part 2, I ran a DRAM test that passed multiple times. So I thought the RAM was fine until I tried to load something from disk. I get a directory just fine, but if I try to load something, obviously that's not good. So I started digging to find the reason for this. The timeout board told me that the problem was in the upper 16K, and the occasional startup with only 16K of available RAM seemed to confirm that. So I wanted to test the RAM with something other than the DRAM test that I was running before. So we can come in here to the monitor, and I'm going to use the fill command to fill from 4000 to 7FFF. That's the entire bank of 16K. Fill that with FF. Takes a second, and then we can do a D. And look at the RAM. And of course, there it is. It's all FF, just like it should be. But what if we change one byte? Let's just change 4010 with a 0. Now we see all these bytes changed. 4010 is a 0, and from 4040 on you see FF, but these bytes all changed to DF. Well, that's not supposed to happen. I only told it to change 4010. If we fill from 4000 to 4FFF with 0, you see they're all zeros. And now let's put a FF in 4010. So 4010 did change to FF, but all these other bytes changed to 20. 20 in hexadecimal is 32 in decimal, and in binary that is just bit 5. If we keep looking, we'll see this pattern: 20 and then zeros and then 20s and then zeros and then 20s and then zeros. Every 64 bytes the pattern changes, and it alternates, and apparently if we write to any place in memory, it'll change bit 5 for all these places in memory. So we definitely have some bad system RAM on the board in the upper 16K. And so it looks like bit 5 in the upper 16K of RAM has a problem and seems to be ignoring some of the address lines. So how do we narrow down which chip that is? Looking at the schematic here, we see this says upper RAM block. And if you look down here, you'll see D0, D1, D2, D3, 4, 5, 6, and 7. So data bit 5 is right here on UA8. Each of these chips is 16 kilobits, but only 1 bit wide. So the address lines go to all the chips, and when the address is at a certain value, they're all selected to the same value, and each one puts out a single bit. So UA8 is our culprit. We need to pull that out and replace it. I have a few spare 4116 RAM chips and a few sockets. So I'll go ahead and pull the board out, replace that chip, and see if that solves the problem. Well, that's unfortunate. I didn't torque down very hard, but I snapped that standoff right off. That sucks. For some reason, this standoff is aluminum, while the others are steel. I managed to get a bit of thread out of there. Okay, so I'm one standoff short over here, so I have to be careful on this corner. But I've got everything reconnected, including the switches here. The RAM board isn't needed to start up in PET mode, or even in 6809 mode. It's just needed to run applications. So let's see if I can load from disk now. We have all 32K of RAM. I have the RAM board reinstalled now, so I can try running diagnostics against this RAM. This ROM socket is just hanging off the wire until I can get some parts to fix that. I have the PET on the table here close enough to the wall so that when I open it up, it rests against the wall. There's a few programs on here: SuperPET RAM ROM, SuperPET Test, and SuperPET RAM. Showing a failure on bank D. ROM shows okay, display RAM, and system RAM showing okay. This program looks helpful. Bank 0 through 15, and at the moment it's showing bit 7 bad on 4 different banks. This is counting through the addresses pretty slowly, so this is going to take a while to run. Now we have bit 6 and 7 bad, and bit 0 on bank 4 through 7, bit 7 and 0 on bank 12 through 15, and now we have bit 6 bad on bank 12 through 15. Looking at the schematic, this top row here, U29 through U36, is bank 0 through bank 3. Bank 4 through 7 is here, U37 through 44. And this row is bit 7, 6, and this row is bit 0. So U37, 38, and 44. And then bank 12 through 15, 53, 54, and 60. I only have 3 spare 4116s left, so I'll go ahead and replace 3 of the bad DRAM chips on the RAM board and see if the tests start passing that bank. But I won't bore you with watching me desolder chips anymore. Here's the RAM board reinstalled with my last 3 spare chips. And here's the retest. And either I was totally wrong about which chips are which, or there's something else going on. Okay, so disregard everything I said earlier about which banks belong to which row of chips. I pulled out the chips that I just replaced and left those sockets empty, and then I ended up with bad bits on banks 2, 3, 10, and 11, which weren't bad before. So my new theory is bank 0, 1, 8, and 9 belong on row 1. 2, 3, 10, and 11 are obviously on row 2. So the chips I need to replace are bits 6 and 7 on row 3 and bit 0 on row 4. And there we go. Finally, it's not showing any bad bits now. Of course, I don't know how far along it is in the test at this point, because it's not printing any addresses because it's not detecting any bad bits. So for future reference, the chips on this row didn't have anything wrong with them. I didn't need to socket those. The bad bits were 7 and 6 on row 3 and bit 0 on row 4. So when I was seeing bad bits on banks 4, 5, 6, and 7, I was actually seeing bad bits on this row and this row, not this one. I want to try loading a couple of other diagnostics programs that I found that run on the 6809 side. This program tests the main 32K system RAM on the PET board. And we passed that test at least one time. This test should test the 64K board. Now all that's really left to deal with are these option ROM sockets. The pins on this plug were pretty messed up, so I desoldered it from the socket there. I found this part online, which looked like it was a pretty good match, but unfortunately the pins are way too short. So I'm waiting for parts on this one. You can see on this socket here that pin 20 is cut off, and this wire is normally connected to pin 20 on the board side. So the switch connects or disconnects pin 20, which is the chip select for the ROM. When the switch is disconnected, it's pulled high with this resistor, and that disables the ROM. So why do you even need that switch? Ordinarily, the PET side system ROMs are turned on and off with this no ROM signal when you switch into 6809 mode. The problem is that most option ROMs for different software back in the day were EEPROMs. EEPROMs usually don't have a second chip select line, so they're not compatible with the no ROM signal. So for the option ROM sockets, Commodore just put a switch in right here on the primary chip select line. UD11 and UD12 are the normally empty option ROM sockets, sometimes used for professional business software like Paperclip. This PET's missing the switch for UD11, but UD12 is a special case because 9000 to 9FFF is the address space where the 64K of banked RAM resides. The reason this PET is missing that switch is that whoever owned this PET before created a special adapter socket for UD11. This is a quad input NAND gate, and this is designed specifically for a 2516. It takes the no ROM signal on pin 21 and inverts it to pin 18 on the EEPROM. Pin 18 is disconnected from the system board. That has the effect of using the no ROM signal to power down the EEPROM, so no switch is needed. Well, I forgot to turn the microphone on for this section, so I'm recording this voiceover in post. This part that I bought before, the pins are too short on it, so I got this pin header type plug instead. And I need to solder this red wire onto pin 20. So 24, 23, 22, 21, 20, and 24, 23, 22, 21, 20. Used to go right there, and I need to press it down as far as I can because I need to cut off the top section of that pin. A little solder on the pin there. Solder the wire down. clip off the top of that pin. And I put a small zip tie on there to strain relief that wire. I need to solder these pins together. One set of pins will be on the outside and the other will be on the inside. Got to get them lined up just right. Not all the pins are the same length, so it doesn't quite sit even. First I'll tack on a couple of pins quickly to stabilize it, and then I'll go back and solder the rest of the pins as neatly as I can. I ended up making a solder bridge between these two pins here. I had to go back and clean that up. I toned out all the pins all the way up to the chip legs, and then I toned out pin 20 with the switch on and off. And here's the final result. Doesn't look pretty, but it should work fine. UD12 is the one way up here. That's secure. Put the switch in here. And this special adapter socket for UD11, there was some corrosion, but I was able to take this thing apart and clean those contacts. I'm going to go ahead and reuse this. This standoff here that broke off, I went ahead and screwed it onto the board there so that even though it's not screwed down below, at least it provides some support for this board. Now you may have noticed something new installed up here. This is a memory management unit for OS 9, which is an operating system that's available for the SuperPET. I built this a few days ago so that I could demo OS 9 for you towards the end of this video. Now it's finally all put back together. So the switches on side here, if I understand them correctly, this switch refers to the 64K of RAM on that top board. Read-only, read-write, and program selectable. There's a register you can write to that will write protect the RAM. Normally this would be left in read-write position. This switch selects between the 6809 and the 6502, or program selectable. You can write to a register that will switch between the two. And this refers to UD12, whether it is the bank selectable 64K of RAM or the option ROM that's installed. The switch for UD11 is missing because we have that special socket in there that responds to the no RAM signal. Now that it's all put back together and working, fingers crossed, why don't I show you around a little bit. Again, I'm no expert on the SuperPET, but I'll try to demo what I've learned so far. I have the 4040 dual drive hooked up because on the SuperPET side of things it's quite helpful to have a dual drive. You'll see why in a minute. I assume most of you are familiar with the PET side of things. This is a standard 8032 with a couple of exceptions. There's a 6551 UART for the serial port here. This is accessible on the PET side. And this 64K of RAM is accessible on the PET side as well. Let's switch over to the 6809 and we're greeted with the Waterloo Microsystems menu. Starting at the top we have setup. We can type the first letter or the first few letters. This takes us into the serial port setup. The monitor is the machine language monitor. The setup and monitor options are in ROM, but the rest of the options require disks. So I've created a copy of the Waterloo language disks, and I'm putting that in disk 1, or drive 1. If we type BAS and press enter, we'll see now it's trying to load BASIC from drive 1. It defaults to drive 1, not drive 0 for some reason. And there we are in Waterloo MicroBasic. And I was surprised to see the screen editor works in this mode. You can type FOR for Fortran. Waterloo Micro Fortran. Now I'll admit, I haven't spent any time with Fortran, so I don't really know what I'm doing here. But I can post a link down below to my friend Dave McMurtry's Twitter post where he wrote a Hello World program in all of these languages. Whenever you enter a selection on the menu here, all it's doing is looking for that file name on the disk. So if you have an SD card reader like this one, it doesn't have a drive 1. In that case, what we have to do is type in disk and give it a number, drive 8 or drive 9. My SD card reader is set to drive 9 now, so disk 9. If we just say disk, it defaults to 8. Slash and the drive number, 0 or 1. On an SD card reader, there's only drive 0. And then the name of the program, like Pascal. Now we're loading from the SD card instead of the disk. These do take a while to load. Waterloo Micro Pascal. And even though it's not on the list, you can actually type in the name of any program you want to load here, like COBOL. There's an operating system available for the SuperPET OS 9, and unfortunately the way this software works, it can't run from an SD card because it requires the REL file type. And it defaults to drive 0. OS 9 won't run on an unmodified SuperPET. You need that MMU unit that I showed earlier. That plugs into the 6809 socket and controls the banking so that the 6809 can access all 64K of RAM at once. And it's asking for the date. I like to pretend it's a vintage date with vintage computers. So let's say 86. And here we are in the OS 9 shell. OS 9 is a Unix-like multitasking, multi-user disk-based operating system. It has subdirectories. This is a list of disk-based commands. You can hook up a terminal to the serial port via null modem cable. And we're multi-user. Well, I guess that's about it for now. I hope you've enjoyed this look at the Commodore SuperPET. Thanks for watching.